Hello everybody, let's look at question number 36 of the 2020 question paper. The transition metal complexes with zero magnetic moment, zero dipole moment and a crystal field stabilization energy of minus 2.4 delta O, delta octahedron R. So 4 transition metal complexes are given, and out of these 4 complexes we have to choose those complexes which has zero magnetic moment, zero dipole moment and a crystal field stabilization of minus 2.4 delta O. Now, how will complexes have zero magnetic moment? Those complexes which do not have unpaired electrons. So the complex should not have any unpaired d electrons. In that case, we will have a zero magnetic moment for the complex. For a dipole moment, see, dipole moment is a measure of polarity of the molecule. So the individual bonds in a molecule may be polar, but when you look at the molecule as a whole, maybe these individual polar bonds, they might get cancelled out because of the geometry or the symmetry of the molecule. The individual dipoles will get cancelled and the overall molecule will have a zero dipole moment. So we have to look at that aspect, which of these complexes have more symmetry involved in it. And then we will calculate the individual the crystal field stabilization energy for the individual complexes. So let us look at the first complex, the manganese complex. It has 5 carbonyl ligands and 1 methyl ligand. It's an octahedral complex, and in fact all of these 4 complexes, they are octahedral complexes with 6 ligands. Now this 5 carbonyl, if you look at in the octahedral environment, we can say it, let's say it occupies these 5. Okay, it can occupy any of the five coordination sites, and the 6th site is occupied by the methyl. Here the 6th site is occupied by the methyl. Now here they are all the carbonyls, so the dipoles, they might get cancelled out in this direction because they are all oppositely placed, so they get cancelled out. But in this direction we have the methyl on top and we have the carbonyl ligand at the bottom. So this bond and this bond, the methyl bond, the bond of the metal with the methyl and the metal with the carbonyl, they definitely have a dipole and they cannot get cancelled out because they are not symmetrical. So that means this molecule definitely has a dipole moment. So obviously this manganese is out of our choice. But just for the sake of it, let's say if it has a zero magnetic moment. So for that we need to know the configuration of this, the d electron configuration for this metal ion. Carbonyl is a neutral ligand. Methyl is an anionic ligand, so that makes the manganese a +1 in a +1 oxidation state. So the manganese +1 is actually a D6 electron configuration. Manganese +1 is D6. Now, if you have a D6 electron configuration in an octahedral environment, we know that the 5 degenerate d orbitals, the spherically symmetrical d orbitals, in the presence of negative ligands or the point charges, negative point charges or the ligands, they split into 2 sets, of T2Gs and EGs. Now the T2Gs are triply degenerate, which consists of the DXY, the DYZ and the DXZ orbitals, and the EGs are doubly degenerate, which consists of the DX square minus Y square and the DZ square orbitals. The T2Gs are more stabilized by minus 0.4 delta O, and the EGs are destabilized by a plus 0.6 delta O. So in such a split environment where the d orbitals are split in an octahedral environment, the d6, the 6 d electrons will occupy the 3 T2G, considering them all as low spin complexes, because carbonyl, methyl, they are all strong field ligands. Ligands mostly with a carbon or a nitrogen donor, they are mostly strong field ligands. So these are strong field ligands, and so we'll have low spin complexes. All of these actually, they'll be low spin complexes. So the 6d electrons will be occupying the T2G orbital. So we will be getting 3 sets of paired electrons. So there is no unpaired electrons here. So that means this complex will have zero magnetic moment. And crystal field stabilization energy is, how do we calculate crystal field stabilization energy? It is the number of electrons in T2G multiplied by minus 0.4 plus number of electrons in Eg multiplied by plus 0.6. So here we have 6 electrons in T2G. So 6 multiplied by minus 0.4 will give you minus 2.4 delta O. So that is also okay. The crystal field stabilization energy is 2.4. The magnetic moment is 0, but the dipole moment is not 0. So this is out of our options. Let's look at option B now. Option B is a nickel complex with ethylene diamine and chloride ligands. Ethylene diamine is a neutral ligand. Chlorine is anionic. Two chlorines, that means we will have a nickel 2 plus complex. So a nickel 2 plus will have a D8 electronic configuration. Now a D8 electronic configuration in an octahedral environment, you will have 6 electrons in T2Gs and 2 in the Eg. So 2, that means 2 Eg electrons means singly occupied Eg orbitals. So each of the Eg orbital will have 1 electron. So the nickel complex has 2 unpaired electrons. So that means the magnetic moment is not a zero number. So it will definitely have a magnetic moment because it has 2 unpaired electrons. It is not, the magnetic moment is not zero. The dipole moment, however, is zero because if you look at the ethylene diamine is a bidentate ligand. So you can consider the 2 ethylene diamine, let's say it occupies the XY plane, the 4 sites on the XY plane. And the 2 chlorine, you can say 1 chlorine is above the plane and 1 chlorine is below. And so it has a nice symmetry here. So the individual dipoles can be cancelled out. So in that case, this molecule will have zero dipole moment. So it does not have any dipole moment. Now the crystal field stabilization energy, let's calculate that. 6 electrons in Q2G, 6 multiplied by minus 0.4 plus 2 multiplied by plus 0.6, which will give us a crystal field stabilization energy of minus 1.2 delta O. So that is not fulfilling the criteria. So the CFSE is not fulfilling the criteria. The the magnetic moment also doesn't fulfill the criteria. Only the dipole moment is okay. It is 0. Now let's look at the cobalt 3 plus complex. Cobalt 3 plus are also, again, it's a 3 plus because it has 4 cyanides. 4 cyanide, each of this is a anionic ligand. So 4 minuses. And water is a neutral ligand. So 4 minuses, but 4 negative ligands. So that will make the the cobalt plus 4. But then the overall complex has a negative charge. So you have to add that minus 1. So plus 4 minus 1 will give you 3. So cobalt is in a 3 plus oxidation state. So cobalt here is a 3 plus cobalt. So 3 plus cobalt means a D6 electronic configuration. We know we did it with manganese here, which also had a D6. D6 will not have any magnetic moment. Zero magnetic moment because all the 6 electrons will be paired here in the T2G orbitals. The dipole moment will be 0 because if you look at this cobalt complex, we can say the 4 cyanides occupy these 4 and it's a trans complex. So the trans means the 2 water has to be at 180 degree with each other. So the so for trans complexes, generally we have a more symmetrical environment and the dipole moment is 0. So cobalt also has a 0 dipole moment. Let's look at the crystal field stabilization energy. 6 electrons in T2Gs and 0 electron in Eg. So the crystal field stabilization energy is 6 multiplied by minus 0.4, which will give you minus 2.4 delta O. So this is correct. It satisfies the 0 magnetic moment, 0 dipole moment, and the crystal field stabilization energy is also minus 2.4. So that is correct. Let us look at the iron complex now. Iron also has 4 cyanide ligands. 4 cyanide means the iron will become plus 4, but then there's also 2 chloride ligands. So plus 4 and there's another 2. So it's a plus 6. But then the overall complex is 4 minus. So that's 6 minus 4. So it will be a plus 2. So iron here is plus 2. It's a iron plus 2 complex in a plus 2 oxidation state. Now iron plus 2 is a D6 electronic configuration. D6 we know from before that it has 0 magnetic moment. Dipole moment is also 0 because it is a trans complex. The chlorine are above and below. It has to be above and below, or you can put it either like this or like that. Anyways, it has to have a 180 degree angle. So the two chlorides are above and below, and the dipoles of the individual bonds will get cancelled out, so it will not have any dipole moment. The crystal field stabilization energy is also minus 2.4 delta O. So D is also correct. So option C and D are the correct answers. Let's move on to question number 37. A chiral stereoisomers are possible for four compounds, organic compounds are given, and out of this we have to find which of these are achiral. Now what do you mean by achiral? Achiral are compounds which does not have any chirality. That means they can be superimposed on their mirror images. So which does not have chirality, that means they can be superimposed on the mirror image. Whereas chirality includes compounds which cannot be superimposed on its mirror image. Okay, so we have to find achiral compounds. So when we look at these compounds, they are called allenes. When you have double bonds adjacent to each other, we call them allenes. And this allene has two double bonds. We can have 3, 4 and so on. So such allenes with two double bonds, if you look at the central carbon, it is sp hybridized. And the two adjacent carbons, they are sp2 hybridized. At first look, we feel that this is a planar structure. So we might think, okay, it has a center of symmetry, it has symmetry. So it is a chiral compound, right? But actually this is not a flat or planar structure. The central sp hybridoids, like in this figure, the two sp hybrid orbitals, they form the sigma bond with the adjacent carbon atoms, and for the pi bonds it uses its two p unhybridized p orbitals, the py's and the pz's. The py and the pz, they are perpendicular to each other. So for forming the pi bond with this carbon, it will have to, let's say it uses the py orbitals to form a double bond with this particular carbon. So to form double bond with the other carbon, it will have to use the pz orbital, which is out of the plane actually. So that makes these allenes non-planar, means they are slightly twisted compounds. They are not flat, they are slightly twisted. So always keep that in mind. It looks misleading, but the allenes are not flat here. They are slightly twisted. Okay, and now how do you find if such a allene is chiral or not? If the two substituents on the terminal carbons, if the two substituents are different, then that makes this compound chiral. That means it cannot be superimposed. So here we know that two substituents are different. This one is methyl and we have a hydrogen here, which is not shown actually. So the two substituents are different. So if the two substituents are different, then that makes the allene optically active allene. But when the two substituents are the same, then that allene will not be optically active. So we have to check if the carbon has two separate substituents or the same substituent. So here we don't have a same substituent, it's methyl and hydrogen. So this is definitely a chiral allene. It is not a chiral. So this option is out. Also in the case of biphenyls, again we have to be careful. This appears flat, but it is actually not flat. One of the plane is out of the plane of the screen. It is the two phenyl rings are not planar. Actually they are twisted, because the reason why it does it, because the ortho substituents, when you have bulky ortho substituents, then here in the four positions here, the four ortho substituents, we have bulky groups, then it makes it sterically congested. So to avoid the steric interactions or the steric congestion, one of the phenyl rings slightly twists so as to make space for the substituents. So it is not planar, it is twisted. And how do you know if a biphenyl is chiral? Similar to the case of allenes, if the two substituents ortho substituents are the same, then it is not chiral, it is achiral. But if the two ortho substituents are different, then that compound, that biphenyl, will become chiral. So this is chiral. So it is definitely out of our option. It is not an achiral compound, just like the allene. When we look at compound C definitely has a plane of symmetry right here. So they can be superimposed on their mirror images, and so it is an achiral compound. So option C is correct. Option D again has a plane of symmetry, and so this is again a achiral compound. So D is also correct. So C and D, they are both achiral compounds. So C and D is the correct answer. So moving to question number 38. The compounds which have only two signals in the proton NMR spectrum in a 3:2 ratio are. So four compounds, again four organic compounds, and we have to find their NMR spectrums. Which of these compounds will give a NMR spectrum with only two signals, and those two signals have to be in a 3:2 ratio. So first we will find those compounds which gives two signals. So let's look at this. This definitely will not give us two signals because we have this two ortho protons here which will give us one signal. So this is similar, but this is not similar to this. This definitely will give these two is not in the same environment as these two. So one signal from these two, another signal from these two, and the third signal from the methyl. So we'll have a total of three NMR signals here. And let's look at the ratio. 3 plus 3, 6 protons from here, 2 protons from here, and 2 protons from here. So 6 is to 2 is to 2. So that is a 3:1 ratio. So out of our choice. Out of the option is not correct. Now let's look at B. B again, we'll get one signal for this proton here, and these two protons are again different from this, so we'll get another signal for these two proton, another signal for this proton which is also very different from these two and this. So 1 2 3 signals here, and the fourth signal from the two methyls. So we'll get four signal here, and the ratios are here 3 plus 3 6, right? Two methyl groups, so 6 protons here, 6 and 2 from here, and 1 and 1. So 6 is to 2 is to 1 is to 1. Now compound compound C, again see this has a symmetry. Actually this and this is the same, and this is also in a similar magnetic environment. So that means all these four protons will give us one single peak, and this methyl will also give us one single peak, and this methyl and this particular methyl is also in a magnetically equivalent environment. So two signals from these four protons and one from this six methyl group. So 4 is to 6, that means 2 is to 3 or 3 is to 2 ratio. So this is correct. C is correct. D is also correct because these two are equivalent. So we'll get one signal for these two, and the two methyl groups will also give us one signal. So 4 protons here and 6 protons from the methyl, 4 is to 6, which gives us a 2 is to 3 or a 3 is to 2 ratio. So these two options C and D are correct. So moving on to question number 39. The correct sequence of reactions for the synthesis of the following molecules are. So we have to synthesize this particular compound. So this has to be the product of our synthesis. So for getting this product, which of the synthetic pathways will we have to adopt? Which of the pathway is correct? So which of these reactions will end up giving this particular product? So I have in the next slide I have shown the product for each of these reaction sets. Okay, so let's look at them one by one. So go starting with the set A. So set A, the first step here, we have the iodophenol, the 4-iodophenol reacting with magnesium in either. This is clearly the formation of a Grignard reagent, RMGI. So we get the Grignard reagent. And now next step is the carboxaldehyde, the cyclopropane carboxaldehyde with the aldehyde group, the cyclopropane with an aldehyde group. We react it with this Grignard reagent. And this will insert into the CMG bond here. So we'll have a CH, a product like this. Okay, because the magnesium which is positive will attack the carbonyl, there's a carbonyl group here with the carbon slightly positive and the oxygen slightly negative. So the magnesium which is slightly positive will attack the oxygen which is negative, and we'll get the OMGI, and the carbon here is partially negative. So this carbon will attack the positive carbon here. So we'll get a compound like this. And this on hydrolysis will hydrolyze the OMGI bond and we'll get OH. So this is just one reaction basically. A reaction of the Grignard reagent with carboxyaldehyde will give us this product. And this product, when further methylated, this is a methylating step actually. When you use cesium carbonate and methyl iodide, the base with a methylating agent, you will methylate the OHs and you will end up with OMe and OMe. Now if you look at this and compare it with the product you want, you'll realize that this is not the product you want. So this is wrong actually. Let's look at the set B. You start with a cyclopropane bromine, bromine on the cyclopropane, react it with magnesium, again a Grignard reagent. You end up with this Grignard reagent, and this Grignard reagent you are reacting with 4 carboxaldehyde phenol, or phenol with CHO on the para position. Now when you react, again you will have an insertion. You'll see there's a carbonyl group here which will react with the CMG bond. The MgBr will attack the oxygen, you'll get an OMgBr, and this cyclopropyl group will go on to this carbon here. So you will end up with a product here which on hydrolysis the OMg bond will hydrolyze to give you an OH. That product on methylating with the cesium carbonate and methyl iodide, you will methylate the OH and this OH both. So again, this product here is not like what you wanted or what the question asks for. So this is not correct. Basically, these two products are the same. Two different pathways, but will end up with the same product. Okay, so both A and B are wrong. Let's look at C now. You're starting with 4-iodophenol. You first methylate it. Instead of creating the Grignard reagent, you are methylating it first. So when you methylate it, you will end up with O-methyl. You methylate the OH, you will get this product. And then you form the Grignard reagent. You react it with magnesium in an either medium. You will get an OMGI here. MGI, RMGX. So you will end up with this product. That you react it with the cyclopropane carboxaldehyde. Now there is a carbonyl group C double bond O, which is polar, which will be attacked by this CMG bond, which is again the Mg has a slight positive and the carbon here is slightly negative. It will attack and will give us a product like this, which in hydrolysis will give you the final product like this. And this is correct. If you compare it with the product which we want on the previous slide, you will see that this is the right product. And so option C is also correct. Now let's look at option C is correct. A and B are wrong. Let's look at option D. Option D, starting with a carboxaldehyde, again just like this here, and you get the Grignard reagent here. But then you are reacting with a slightly different reagent. You are reacting it with a methyl 4-methoxybenzoate. So this is methyl benzoate with a 4-methoxy on the 4 position or the para position. So that when you react, again you have a carbonyl C double bond O here, which will react with the CMG bond here. You will end up with a product like this. On hydrolysis, you will give this product. Now this is nowhere near to the product that we want. So this is also wrong. So the right strategy to get a product is option C. So option C is correct. Okay. Now let's move on to question number 40. The organometallic reagent among the following are. 4 reagents are given, and out of which we have to find which of these are organometallic reagents. They are all reagents, but which are organometallic reagents? See, organometallic compounds are compounds which have at least one metal carbon bond. Now, if you look at these 4, this is the lithium divinyl cuprate, the copper with the divinyl, 2 vinyl groups, and it's a lithium salt. Lithium divinyl cuprate, there is definitely a metal carbon bond here. So this is an organometallic reagent. Again here lithium diisopropylamide with 2 isopropyl groups on the nitrogen. This does not have a metal carbon bond, right? So this is not an organometallic reagent. Here again, let's look at this option. There is no metal carbon bond again here. So potassium tertiary butoxide is also not an organometallic reagent. This one here, the isopropyl magnesium iodide, it's actually an organometallic reagent. This is actually the Grignard type of reagent. So this is again an organometallic reagent. So both A and D is the correct option.